Okay, so so in today's video, we can talk about and the regressions. There are two main method and algorithm in linear regressions. One is the ridge regression, another one is lasso. So we're gonna talk and assume like you already know the the model and the concepts of this. And here in this in a notebook, we are just trying to demonstrate how to using the package to and for those models and how to using the cross validations to pick the best parameter for for region and the lasso. So basically, the whole idea for the lasso is and for the ridge is we are going to and impose the L2 penalties to the linear regressions of the mean square error. However, lasso is we're going to and apply the L1 penalty instead. So, and if we are using lasso of the L1 penalty, it will and imposing this and sparsities. And the reason that it's good for the sparsity is if the weight that we got is sparse, that means it automatically select features. So if you automatically select the features, so we can using lasso to pick the features for use. So this is naturally come out of this lasso and then the power of the lasso here. And also the ridge regression is naturally come from and adding the L2 and the penalties to prevent or like mitigate of the overfitting phenomena that you will see. Okay, so here we're going to be just using a data set to illustrate the whole idea. We are going to work a very traditional data set. It's called Boston House price data set. So we're going to load this data set right here. And if we look this data set right here, you can see that the X actually looks like and all these values and the Y and correspondingly. So right here, so if we, it's just, and actually to look at this raw DF, it's quite messy. So you actually need to make sure this is being and processed correctly. And there's a lot of like null values and so on. And you have to be and careful on this. All right, so so basically this is and the data collected like a long time ago, and you can see they have like a bunch of variables here. So it has all the and all sorts of different variables here. But if we look at this and the data, and they have various different scales, and you can see some scale is 10 to the minus 2, 10 to the minus 3. Some scale is 10 like and 10 to the 2 and so on. So it actually represents different scales right here. So and you have to keep in mind and like we are and dealing with like and a different and various different features with a different and for those variables. So okay, so and for lasso that actually minimize the mean square error with L1 and the regularization. So this is basically your mean square error. This is your L1 regularization with an L1 norm. And you can think about in lasso, this is my model, and then so my model is simple linear regression. It's W transform of X. So like W inner product of X. That is and basically a hyperplane. It's a linear model. So it actually depends on the model parameter. That's we trying to infer right here. Since we imposing this L1 penalty, this ensure this W has a strong and a sparsity, and that means and a lot of and W right here will be in the zeros if if our alpha sufficiently large. All right. So and what we can do is we can fit the lassos with and a small alpha coefficient with and a small alpha that indicate we have and weak and regularizations. So if we do this with alpha equal to 0.1, you will find out, and we do the fit, and then we find out the coefficients. And we find out for the fifth features, which corresponding to NOx, like that would be and precisely equal to 0. So this is nitro oxidized concentrations will be 0. So that indicates with weak regularizations, the LASSO think this coefficient is not important. And also this gives you some idea and help you to do the feature selections. So, and that tells you for this linear simple linear models with the LASSO, it tells you this feature is not important. So that means if you want to apply to more complicated models, you probably shouldn't even consider these features, because I mean it's very, and then it's a natural and extension coming from the feature selections, and coming to the feature selections. So that means this feature is least important for this median house pricing predictions in this region. So and I mean, so a very simple way to say is we're going to throw this out. And also, so then we are going to train this LASSOs with a fairly strong regularization with alpha equal to 10. Then you will see almost all coefficient right here will be 0, except for this one, this one, this one, this one. This is basically the 4 things and the left out. So and then that corresponding to proportion of the residential land zone lot over 25,000 square feet. Tax, which is full value property tax rate, proportion of black by ton, and like LASSO, which is the percentage of lower status of population. So basically, these 4 features is the features they consider to be important in this data set. So so as you can see right here, so if you want to using like fewer features to predict the house pricing, maybe you probably should choose these 4 features instead. So these 4 features and this and the LASSO regularization, you can think about and it can be served as feature selection methods. All right, so and what we can do is we can create something called like the regularization path. So what does that mean is I'm going to like and change my regularization linearly from 0.1 to 10 with a 200 different of that. So and for each of alpha, which is and represent each like regularization coefficient, I'm going to set this parameter for this alpha equal to this corresponding and alpha ranging from 0.1 to 10. Then we're going to fit that, and we are going to store these coefficients. So the way to visualize and what we're going to do is we're going to visualize the coefficients. That can tells us when this and features is important and when the feature is not important. So you can see this is something called regularization path. And up to this point right here, and which is 0.1, so you will see the most of features is not equal to 0, and as far as alpha getting larger and larger, and many other features was muted, and it goes to 0 precisely, up to say like 10. That means there are only like very limited features being left out here. So this tells you like in LASSOs, as the regularization is getting larger and larger, and more and the coefficients will be zeroed out. So that means the coefficients or the weight being like 0. And eventually you are hitting like and super strong and the regularizations, then everything else and every and the coefficient will goes to 0s. Okay, so and what we can do is we can using this cross validation method to find out what is the best alphas that and we can choose from. Here, what we do is we are going to choose this alphas. I think this is my alphas right here, which is 2,000 and alphas from 0.1 to 10, that's the range that we want to find for the best alphas that we can find. So here is the and what we can do is we're going to using threefold cross validation to find out the best possible alpha right here, and that's the corresponding and the coefficients, and that's corresponding alpha here. So what they do is, and they are going to using and the threefold cross validations using this and the validation error, and average and validation errors as your scoring point to find out the optimal parameters for the lassos right here. And turns out the way you find it out is this an optimal like alpha here is 0.15-ish, and this is and that's the corresponding coefficient right here, and that indicate almost everything is important except for I believe the NOx. For that one should be and muted out. I mean, that one is not important. Okay. And also, so we can find out this and the scores as well, right? So we want to find out the scores. So what we can do is we are going to using this like lassos and models with optimal alpha and the values right here, and we are going to do this threefold cross validations to find out and the mean square error. But usually, I mean, as a metric in the scikit-learn, I mean this and this should be and the metric should be maximized. So what they do is they are going to take a run and put them in a negative signs, and then like an negative like mean square errors will be like and trying to maximize that part, and that will be equivalent to minimize the mean square error as well. Which in this case is you will see it's all coming with the negative values. So you will see the negative values ranging from -16, -37, and -72. So this actually gives you the square error, and the mean square error is 42 instead, right? So of course you can choose different and the lasso values. I mean, instead of choosing like 0.15, you can choose other one, for example, 9.95. Then the average and the cross validation and an average mean square error in this, in this parameters that will be 53.72. So that one is like significantly bigger than this optimal alphas. So and that just indicate and this is truly the optimal like alphas that we should be choosing here. All right, so and also there's a one ambiguity point that you have to be careful here. So this like lasso CV actually saw the values of the parameters in a decreasing order. So this will make the optimization a little bit easier. So like that was seems like this like and optimization works incorrectly. So this is because I mean if you actually look this alpha right here, this is from 0.1 and the first 10 of that is starting and from 0.1 right here. But if we look this alpha S, which is and the one being actually stored in the cross validations, it's being stored in the decreasing orders instead of like and the increasing orders. So this actually gives you some like different ideas. So you will find out, and this is, and they are using, and if you, I mean, if you want to calculate the like, and the so MSE path and path corresponding to the alphas, you should not using this like lasso CV and alphas right here because this is for the increasing orders. But for this like MSE path, what like and the lasso CV is doing is they're trying to do things in a decreasing order. So instead, what you should be doing is you should using this and alphas with underline right here, and this is actually the and a correct like command line right here. So this actually and plots this and as MSE for this problem and versus this and the regularization and the coefficients of alpha right here. So you can see the actual and the minimum MSE is being chosen at this point right here, and which is about like slightly above 42 here. So you can see this whole path is pretty zigzag. It's never been any like one peak, and they have like multiple peak possibly. So right here, and what they do is they just doing a simple search and a grid search to find out the optimal parameter such that minimize this MSE right here. Right here, okay? So, and I mean, so if you want to plot this like, and the alpha versus, the MSE, you should be using this alphas with underline instead of the one and above. That one is incorrect. All right. So this is LASSO, and also like, and the other one is the ridge regression. So this is very simple. Instead of you using L1 and the regularization, and here we're using L2 regularizations. So everything else is basically the same. So here what we're trying to do is we're going to trying to set up this like enrich alphas from 10 to the -2 to the 10 to the 6. So this is a pretty and large and ranges here. So if the ranges change so dramatically, so what you are going to do, and what we usually do is we're going to take the log space instead. So basically, is we're going to and the linear space between -2 to 6. Then we're going to use 10 and a power of tens, and such that these scales are in terms and that and will be in the log scales and the log linear scales. So you can see like this is basically to tells you how this and the scales look like. It's a really bad idea to choose and to space these scales like linearly for 10 to the -2 and to 10 to the 6, because if you do linearly, and most of things are being and alpha will be concentrated into very large numbers, such that those 10 to the -2, 10 to the -1, 10, and then like 10 to the zeros, and all these of that, and most of them will be just simply ignored. So and the best way that we should do is the log space here, and everything is being the same. We're trying to using like enrich CV to do the cross validation to find out the best parameter of alpha and for this type of problem. And this is the scoring here is again is negative mean square error right here, and we have rich alpha right here. Okay, so if we do this and we find out the best alpha that we can get is 264. So this is the alpha that we get. And we can also find out that and the corresponding coefficients, and you will find out these coefficients are like going to be close to 0, but they are not, and they're just small values, but like non-zeros. And you can also create this kind of like regularization path, like what we had. LASSOs, it will be doing like this. So and you will see at any point right here, for this alpha here, it will always be like strictly positive. It will be like strictly non-zero right here, and at any of the alpha here. And asymptotically, if you let alpha goes to infinity, so they all goes to zeros. Right? So this is what you should be getting here. So the ridge regression is like pretty straightforward, and the stronger of the larger of the alpha, the stronger of the regularizations, and it will be and more to be more like underfittings, the smaller of the alpha, which is weaker and regularization, and that will corresponding to the and more toward to the overfitting regions. Okay, so this is the ridge regression right here. Okay, so that's that part. This is very simple and introductions to those and the ridge and the lassos. And next, what we're going to do is we're going to talk about one case studies. So and from now on, I'm going to talk about a bunch of the case study problems. This one quality problem is one of that for sure, and in fact, there will be more and case studies will be talked later of the courses. One of the reasons that I want to talk about this is just because a lot of cases when we and talk about all these models, that we just focus on these models. We don't usually focus on the data. But in the practical machine learning, it should always focus on the data, because you can use all sorts of different models. You can use all sorts of different pre-processing. You can use all sorts of different feature engineering, but the ultimate goal is you want to using all and various different methods to achieve your certain goals. And you need to set up your metric. You want to and make sure after this process and you are achieving the best result possible. And you will see and later on your courses, and I will not specify what kind of model you should use. In fact, there will be free ride. You can do whatever things you want as fast as you can achieve certain level of accuracies, right? So this is the goal. And which method you should be using that, that actually doesn't matter. So that's why, and we're going to talk about a bunch of case studies, and we're going to using various different methods, and actually give you some idea what you should be encountered during those kind of realistic data set. So this is the very realistic data set for its one quality data set. So this is a very small data set. So this actually related to this red and white one. And they have bunch of details. You can click that to see some references here. So they have all these different features that we're getting here. So for example, the fixed exit and the volatile exit and the sidetrack and exit and they are various and a bunch of different input variables right here. The output variables is the qualities. So basically, this quality is ranging from 0 to 10. And of course, basically, we can think about this as being and regression problems. You should never think about this problem as the classification problems. And although you could, but because this quality actually ranges from bad to good, right? So and a 0 and that implies it's bad. 10 implies this is good. And they should have monotonically and increasing from 0 to 10, and as a quality of this ones. So if one is 7, another one is a quality is 5. That means 7 is better than 5. So there will be metric involved. Instead, for the MNIST data set, we are trying to classify from 0, 1, 2, and until 9 for the digits. If we classify one image to be 5, another image to be 7, that doesn't mean 7 is bigger than 5. It's just a placeholder to call this image to be 7. But that doesn't mean this image is better than the image of the 5. That's two different things. But here, since we are talking about a quality, actually we can say this one with the quality of 7 is better than the quality of 5, and the one with the quality scores being 5. Okay, so this is actually the data, and you can see this is data has all these features. The last columns will be the target that we're trying to get. Okay, so you can see we have 10 features, and the last feature, and the last one will be the target, and which is integer. The other like 11 and the features that we have, they're all float, and there's no null data that we have, so that's good. We don't need to and pre-processing that part, so that will be good. So the first things that we need to do is pre-processing. And since we only get one data, we need to split the data with 70% of training and 30% of testing. So this is what we do. So we're going to do the train test split for the 30% of testing, 70% of training. And then what we do is we need to scale the data. As you can see right here, we can see all these parameters has a different scales. And for example, for this one, this has a scale and around 0.3. And for this like features, a scale with hundreds. So that means and for the suitable and for the best performance of the machine learning model, and we should try to do standardization of these part. So what we're going to do is we're going to create a standard scalar. This is very important. You're going to train the scalars on the training data set, X-train, and you're going to apply the same scalars on our holdout data set, right? So you should never using fit transform on this command line right here. And we can only do this fit transform for the training and a transform on the holdout in the data set. We need to apply the same scalar on the both training and the holdout data set. All right, so the first thing is we need to train a very simple thing, since this is basically a regression problem. And the first thing that you should try is just ordinary like least square. So we're gonna do like linear regression right here and train this training data set. And so X-train scale, so like that's the, and rescale the data set. And the target will be my Y train right here. So this training error is getting a 0.558. On the other hand, and we can test with our holdout data set. The holdout data set tells me the error, and the testing error is 0.58. So you can see this is quite big. So that means the error, training error and testing error are both quite big. So that means this is in the region of underfittings. So that means we have a lot of room to improve and to have better models for this type of problems. And of course, you never and expect and the linear regression will always do the best work for you. But before you move on, and there's one thing that you can think about this, can we tell anything on like just simple least square, right? So, and what we can do is we can sort the features by their inferences on the targeted features. So that means I'm emphasize if your coefficient is like large positive or large negative, that means that has a large inference on our target. If this coefficient is small, that means it has small inference on the target. So that means what we're trying to do is we can using this panda like data frame here, just trying to see and take the absolute values to see which feature has the most influence on this one qualities. So if we do this, we find out, okay, the density and the residue sugar and the volatile so acid, they are all like very important, and they have like very large inferences, whether it's positive or negative, but they still have the largest inferences to the quality of the wine. And however, those like and a citric acid and a chloride and a total sulfur dioxide, these have a very small weight. So that means just coming from this least squares, that indicate these features are not that important. So it has a like less inference to this one qualities. But that doesn't mean too much. So we know and our least square and right here could just be like simple like underfittings. All like all this like and it's not doing a very good job right here. So let's try something more. For example, we can try like lasso here. So for lasso, we can try with a different one. For example, we choose alpha to be 0.01, which is like very weak regularizations on this scale data. So we do this whole things again. Then we find out the actual one for the lassos with the very weak regularizations. Alcohol, like residue sugar and density are top three and the most influential and features to those qualities of the ones. On the bottoms, you will find out the fixed acid and the citric acid and total sulfur dioxide. These three actually the weight it just goes to zero. So that indicate I have zero and inferences to those qualities. And you can see, and for these things, and they have some overlap right here. For example, citric acid, and we have a citric acid in the least square as well. We have a total sulfur dioxide, and we have a total sulfur dioxide in the lasso as well. So I mean, basically these two things and like both model for the lasso and the least square tells me these two features are not important. However, for the regular sugar and the density here, and here we also have a regular sugar and the densities. So these two features, they both shows and they are top three important in both models, in lasso and the least squares. All right, so, and of course, we just randomly choose alpha to be 0.01, which corresponding to the weak regularizations. And like we can also choose and using the cross-validation to find out the best alpha if we can. So here we're going to train this lasso CV and choose the best values alpha in this five-fold cross-validations. Under these things, then we find out which feature is, least informative and which one is the best and the most informative. With this tuned lasso models, with the tuned and this lasso models, that just indicate that this is the, and at least for the lasso model, that would be the best lasso models we are getting here. All right, so so this is the lasso right here. So and so once we run this, we're getting the best alpha is chosen at almost like 2.8 to the 10 to the minus 4. We do this calculation, we find out these top three is basically the same density and the residue sugar and the volatile and acidity. And these three is basically the same as the least square, right? So these are the same as the least square. The bottom one, the one that is the least important right here is like citric acid, right? I mean, this is basically what we're trying to do for the citric acid. So that means we should get rid of this citric acid. So this, citric acid is really not important. But when we do this like training and testings, do the same things again, we find out that this like mean square error and the test on the training and the validation, they're all like very close to each other. And the value is still very close to the least square, right? So, I mean, it's not much improving here. Yeah, there's not much improving. I think they only improve like 0.001, something like that, right? So it only improved by 0.001 by getting rid of this total sulfur, by getting rid of this and the citric acid. So this just tells you, this citric acid is really, really not the most important and not important at all. And we should completely get rid of this. All right, so that's good. So the next is we can do some more complicated models. For example, one of the complicated models that we can use is the random forest. So this is an like ensemble method. We can talk, and we are going to talk about this like ensemble method and later on. But I just want to emphasize right here, we are using this lasso right here just to pick the like features. So basically through this like analysis, we can confirm we should get rid of this like N-citric acid. But that doesn't mean like the other like and features are still very important. I mean, it's possible the other combinations of and we're getting like better result if like and possible, but just coming from the lassos says and every other features, and we are going to and keep every other features and get rid of the citric acid. But that just saying again, that just saying that's the result coming from lassos. If you're using like random forest to do the feature selection, I think in the like previous videos we already mentioned there are two main methods to do feature selections: lasso or the random forest. We can use in random forest as well. It might create or give you completely different results, right? So this is all up to the like the method that you choose. So here, so and here what we're trying to do is, and we're trying to do this like in a random forest way. So we're gonna ask what is the mean square error. I mean, if we build the random forest models on the trainings, also we do this cross validation as well, and we want to see the errors on the holdout set. So then we're going to tune the maximum feature as maximum depth on the grid search, and check what is the and the mean like cross validations and also on the holdout set with the like optimal parameter here. And also I will ask what are the mean square errors for this tuned and random forest in the cross validations, and same thing. At the end, I'm going to ask what is the most important features according to the random forest. So this is pretty straightforward here. Okay, so first thing first, we're going to and just train and the random forest here. We do the fittings. This is what we got for the trainings, and this is what we got on the cross validations and the holdout, right? So this is basically we're using the default and the parameters. We're not tuning any parameters here. So for the training error, it's super small, it's 0.053. The actual validation error is giving me 0.414. So this is the like average threefold cross validations, I believe. Yeah, threefold cross validations. And this is the result for the holdout, which is 0.372. So you can see these two are both pretty big compared to the training. But of course, this error is still significantly smaller than the lassos and the least squares, which is 0.58 here. So yes, random forest is improving, but we might see some like an overfitting problem here, because you can see right here, I mean, with like just a random and a very much random, by default parameters, my training error is super small, but my validation error is significantly bigger. So they have created a big gap between the training error and a validation error. So that indicates, and this random forest may have the problem of overfitting here. But like sometimes it might not be a bad things. So, and what we're going to do is we're going to do some like hyperparameter tuning to find out the best features and best and hyperparameters and for these problems. So we do the grid search, and the parameter that we choose is maximum depth and the maximum features. Then the scoring, and again, will be negative mean square error. That's like always the golden standard in these kind of like and regression problem right here. So that means in total right here, we have 40 different here of the parameters. Here we're trying to do the 5-fold. So that will mean in total, that will be 200 fits. It took 3 minutes to run. The best parameter we're getting is 21 and 6, and the validation error is -3 and minus 0.39 right here. It's still close to and like 0.41, but still, and that will be like slightly better. Then we can try this on the cross validations versus the testing. So you can see they start to be quite close to each other. So this is 0.398, this is 0.366, which is quite good in this case is compared to and better than and what we have right here. So this is 0.372. On this holdout, we are getting 0.366. So I mean it's better now. And also this also give you the whole idea of the feature importance. And we're going to talk about the feature importance over the random forest in the later of the courses. So this just tells you by the random forest and which one is the least important and which one is the most important. And right here we see the alcohol actually is the most important, has the best weight and has the largest weight right here. And on the other hand, sulfurate and fixed acidity and a citric acid. So all these threes are the bottom threes. And they didn't differ too much. You can see these threes are like least and the least important ones. And of course, like citric acid and fixed acidities, they are all showing up in the other models right here. For example, I believe it's fixed acidity and the citric acid. Both are like showing up right here. Both are showing up not in this one, but like I'm showing up right here. It's not showing up here, but it's showing up in the random forest. Basically, the random forest says these three and features are the least inferentials compared to all the other 8 features. So this just gives you some idea. This kind of feature selections is really ad hoc. I mean, it depends on what kind of model you choose and what kind of model that you believe is the most important. And you can try and play with the different models to see and what they are like, and giving you, sometimes it give you and that kind of result. Sometimes it give you different results. And you can see right here, citric acid is also on the bottom 3. That indicate this citric acid is truly not important, and that we shouldn't like keep this features. We should get rid of that, right? So there might be some consensus. They might have some differences. So that's why this kind of practical machine learning problem on this realistic data set, it's really up for you to interpret, right? So it's like really up to you to interpret what kind of result that that we can like give a good stories, and by the end of that to achieve a better and predictions for the models and a better and prediction for the data. So this is very important. And here we're talking about, I mean, this is a case study right here. In the later of videos and the lectures, we are going to keep this kind of format. And once a while, like 3 or 4 lectures, we're going to come back to talk about one very specific case studies. Sometimes that case study will be big. Sometimes that case study was small. And some are related to the homeworks. Some are like just like to demonstrate some concepts. So this will be very, very important. I mean, a lot of cases, this is kind of the center core of the practical machine learning. Okay, so that's all for this one.